Welcome. This is the one to last week of lectures for our applied mathematics course. This week I'm going to be covering the Laplace equation. We're going to be starting that and finishing it next week. And I'm going to cover a brief recap of the Green's function because I noticed that in the second review there was quite some confusion about how to apply it in the case of the Laplace transform. So we'll be covering that topic a little bit. This week's lecture is going to be a bit lighter because half of the week is actually holiday here in US. On Thursday there is Thanksgiving and Friday is Black Friday. So for this reason, this week is roughly half of a usual week worth of material. There are still group assignment, homework, and reading assignment due next week. So let's start. Let's start with the Laplace equation on the rectangle. Last week, we saw the heat equation on the rectangle, and we saw how it can be split into two solutions, the steady state solution and the transit state solution. With the steady state solution having the same boundary conditions as the initial heat equation problem, while the transit state solution has trivial boundary conditions and an initial condition that is the starting initial condition shifted by the solution of the steady state solution. And then, if we have solved for the steady state solution and for the transit state solution, then the solution of the heat equation on the rectangle is the sum of these two elements. And we can do this trick of just splitting things away and solving piece by piece. So solving trivial boundary conditions and non-trivial boundary conditions, or parts of the linear problem and then summing them up, because each of these elements is linear. So U, being the sum of V and W, will solve the full problem because the problem is linear. And we're going to be heavily using this through all of our PDE course, taking advantage of the fact that all the operators we deal with are linear. That's why nonlinear operators are that much harder, because you cannot split it in simpler problems. Or if you do, it needs to be very, very careful how you're doing it. Anyway, now we have the problem of solving the steady state solution. And the steady state solution corresponds to the Laplace equation. So this is a build-up to explain why, in this specific situation, we're interested in solving the Laplace equation. That can be written either as a capital delta V equal to 0 or Laplace squared V equal to 0. Because it comes from the heat equation, it's usual to put a minus sign in front of both operators. Clearly the solution is the same, but it's just a leftover from the heat equation that we try to remember that there is a minus sign in front. In this case, we're going to be solving it on the rectangle, 0a times 0b. We have 0 boundary conditions at the bottom, at the top, and at the left side, and non-zero boundary condition at the right side, where we place some non-constant function, or not necessarily constant function, depending on y. We claim that the solution of this Laplace equation with partially non-trivial boundary conditions can be solved with separation of variables. So we will write v x y as the product of a function x of x and y of y. Remark, we have already used this separation of variables, and depending on the domain that you use, then different coordinates might be useful. So for example, we saw that when we're doing the disk, separation of variables can be used in polar coordinates. Here we have a rectangle, and xy coordinate seems to work very well. But different domains will trigger different variables to separate. Second remark, if we have 0 boundary condition everywhere, then v equal to 0 is a solution, and the Laplace equation has a unique solution, so that is the only solution you should be looking for. So that's why for the heat equation, we started with 0 boundary conditions, while for the Laplace equation, we already start with at least one non-zero boundary condition. So we have our heat equation, we apply the separation of variables, and that means that we want x second y plus xy second equals to 0. And with a similar trick as we did before, that means that the fraction x second divided x is equal to minus y second divided by y. And we set these two equals to a constant. And as a general statement, we now write it plus or minus k squared. This is a different sign than before. And we choose this to keep our options open. Before, it was clear in which direction we wanted to go. Here, because of the boundary conditions being non-trivial, we might want to be a bit more careful about which of the two signs we're going to be choosing. We're going to be seeing further on where the plus or the minus will going to be popping up. And then we're going to come back and choose only that sign. And to be more careful, we'll look at the rectangle on which we have defined things. And if we are cutting a vertical cross sections and only looking at y depending on y, we notice that y depending on y has trivial boundary conditions. So if we're taking our constant equation, we notice that it has a structure of a Sturm-Liouville problem. On the other hand, if we're looking at the xx, so something that cuts on a horizontal cross-section of our rectangle, then the boundary conditions are non-zero at the end, so we'll have to be more careful with it. It's not straightforwardly a Sturm-Liouville problem as we had for the y direction. So that's why when we have the boundary conditions divided in this way, we're going to be starting by solving the y direction, a vertical cross-section that has trivial boundary conditions. So here we go. We want to solve the section regarding the y. So we're looking on our bigger equation at minus y second divided by y equal plus or minus k squared. So if you rephrase it as a Sturm-Liouville problem, that happens to be y second plus or minus k squared y equal to 0. And assuming k to be real, because that's usually what we want to aim for, then we want to put a plus sign there. A plus sign is what we look for the Sturm-Liouville problem. Otherwise, we would have a minus and the weight is negative, and that is not the standard form. So that's why when we go back, we want to check that the sign that we have chosen is a positive sign. So here is why we determine the sign of the k squared in our equation. Because it's a Sturm-Liouville problem, then k squared is real. And we can also go a bit further by noticing by theorem 17.7.2 that k squared is positive, therefore k is real. But at the moment, let's start by just saying that k squared is real. So this freedom of choosing the sign of k makes our job easier. Think about what would happen if we would switch a bit the boundary conditions and we would set v equals to some function of x at the top of a rectangle and 0 everywhere else. Would we choose the same structure? Would we choose always k positive? Maybe we want to change that. But now we have k positive, and we apply the standard approach for the Sturm-Liouville problems. That is, we find a solution depending on k. So we have capital Y of y being a sum of two exponentials depending on k squared. I then introduce mu equals square root of minus k squared. Otherwise, it's really very tiny to write everything down. But in order to satisfy the boundary conditions, then we require that a plus b is equal to 0, and a times exponential of minus mu times b, small b, so the end of a rectangle, plus capital B exponential of mu b, where small b is the end of a rectangle again, is equal to 0. As we do for Sturm-Liouville problems, we rewrite these two equations into a matrix form. So we have a matrix that is 1, 1, and 2 exponentials at the bottom, multiplied by capital A and capital B vector, and we want that to be equal to 0. But we also would like A and B to not be both 0, so what we need is the determinant of this matrix that I just introduced, that I'll call capital M. We need that determinant to be equal to 0. And that corresponds to saying that the exponential of mu b minus the exponential of minus mu b is equal to 0. And this works only if mu is purely imaginary, no real part. And if mu is purely imaginary, then like backtracing, then we need k to be real. Then I rewrite mu as I lambda, such that it is clear that it is only one imaginary component and no real component. And then I can write things out in explicit terms. So we can write that the exponential of I lambda b minus the exponential of minus I lambda b is equal to 0. And we split this and write it as a sum of sines and cosines. So we have cosine lambda b plus imaginary number times sine of lambda b minus cosine lambda b plus I sine lambda b equal to 0. And you notice here that the two cosines cancel out, so we're left with 2I sine lambda b equal to 0, and that means that our lambda is an integer multiple of pi divided by b. So now with this process we can define the eigenpairs. The eigenvalue is kn, that is equal to lambda n, is n pi divided by b, and the eigenfunction is a sine of lambda n times y. So there are countably many eigenpairs, as we expect from a Sturm-Liouville problem. But now that we have solved the Sturm-Liouville problem, then we have determined what is that constant in our x prime divided by x equals to k squared. We have determined it, and now we can solve it. So we have this equation that is x second minus kn that we defined just before from the Sturm-Liouville problem of the y dimension squared times x equals to 0. And this is an equation that we can solve as the sum of two exponentials depending on kn. So a times exponential of minus knx plus b exponential of plus knx. And we can rewrite this with a new formalism. So we introduce the hyperbolic sine and the hyperbolic cosine. The hyperbolic sine is defined as the difference between exponential of x and exponential of minus x, all divided by 2. While the hyperbolic cosine is defined as the sum of exponential of x and exponential of minus x divided by 2. They're called sine and cosine because at 0 the hyperbolic sine is equal to 0, and at 0 the hyperbolic cosine is equal to 1, just to remember which is which. Other than that, they're very different functions. But this formalism really helps us because of the simplifications at 0, simplifying 1 to 0 and the other to 1. The coefficients in the middle have changed, but we don't really care. We don't know them anyway yet. So now we can merge these two solutions. And we can write that Vxy is an infinite sum of all the xn's times all theyn's, 1 by 1 matching. So it's an infinite sum for n equal to 1 to infinity of sine kny multiplied by the sum between a hyperbolic sine and a hyperbolic cosine, both applied at knx with different coefficients in front. What problem does this solve? Well, it does solve the Laplace equation on omega, because each component solves the Laplace equation on omega, and Laplace equation is a linear equation, so if each component solves the Laplace equation, then the sum of all the components solves the Laplace equation. It solves the trivial boundary conditions at the bottom and at the top of our rectangle, but we haven't yet solved the other two boundary conditions, the boundary condition at x equal to 0 and the boundary condition at x equal to a. But we still have a lot of freedom in here because xn is defined with respect to an and bn that we haven't fixed yet. So in choosing the values an and bn, we'll choose them in such a way as to satisfy the two boundary conditions that we haven't satisfied yet. So this slide just does that. It defines psi n as the multiplication of xn and yn. And we check that psi n satisfies the Laplace equation. So psi n, if you take the second derivative with respect to x of psi n, you retrieve kn squared. So on the x direction, you notice that we only have exponentials, and exponentials have this property that the derivative of exponential just spits out the coefficient of the exponent, while the second derivative with respect to y spits out a negative kn squared, because on the y direction there are only the sign, and that gives us a negative sign of the second derivative. So indeed, for every single psi n, the Laplace equation is the Laplace equation equal to 0 is satisfied. So, and as I was saying before, psi n is also satisfying the trivial boundary condition at the bottom and the top. So we have to find the values an and bn for every positive n such that the other two boundary conditions are satisfied. So let's go for it. Let's start by trying to satisfy the left boundary of our rectangle, that is a trivial boundary condition. So we have that 0 is equal to v computed at x equal to 0 and y. That is an infinite sum for n equal to 1 to infinity of an hyperbolic sine of kn times 0 plus bn hyperbolic cosine kn 0, all of this multiplied by sine kn y. Obviously, sine kn y doesn't simplify anymore, but we know that the hyperbolic sine at 0 is equal to 0, so the term multiplied by an disappears, while the term multiplied by bn gets to be 1. So now we only have an infinite sum of bn times sine kn y. But sine of kn y are orthogonal functions. They're linearly independent. So this infinite sum is equal to 0 only if every single part of this infinite sum is equal to 0, and that means that bn needs to be equal to 0. So we're left to define an, and we still have a boundary condition at the other end of the rectangle, so we have f of y equals an infinite sum of an times the hyperbolic sine computed at kn times b times the normal sine computed at kn y. This is a sine Fourier series, so we know how to deal with this. We find that an, so the coefficient of sine kn y, that is an hyperbolic sine kn_b, needs to be equal to the inner product between f and sine kn_y normalized by the inner product of sine kn_y by itself. And here we notice that the hyperbolic sine of kn_b, it's just a constant. So we can divide our right-hand side by the hyperbolic sine computed at kn_b and have an explicit formulation for an. With this, we can write explicitly, albeit we haven't really computed all these ans, but we have a formula for that. We can write that the solution of our Laplace equation with one non-trivial boundary condition is this infinite sum going from 1 to infinity of an hyperbolic sine of knx sine of kny, with kn equal to n times pi divided by b.